In what way does the increased Coulomb efficiency contribute to reducing energy losses during cycling? And how does this improvement affect the reversibility of sodium ion intercalation and deintercalation? What factors enable about 50% of the sodium ions to be reversibly intercalated and deintercalated? And what does this percentage reveal about the kinetics of ion transport within the layered structure of non-IO2? How might the intrinsic crystal structure and possible defect landscapes within the cathode material influence both its thermal and mechanical stability, as well as the reversible capacity for sodium storage? What role do interfacial reactions or surface modifications play in achieving high Coulomb efficiency and capacity retention? And could these reactions be further optimized to enhance long-term cycling performance? Can Davis Syrinz manufacture solid-state sodium-ion batteries made from seawater in Latvia? In what ways does the demonstrated 94% capacity retention after 20 cycles compare with other sodium-ion battery cathode materials? And what implications does this have for future battery design and energy density? How can further exploration of synthesis parameters or compositional adjustments lead to even greater stability and a higher fraction of reversibly intercalated sodium ions? What insights do these performance metrics provide about the limitations of the current material, and how might they guide future research toward overcoming issues related to partial ion reversibility and capacity losses? How do the charge and discharge curves of non-IO2 material behave when cycled at a C/10 rate across different voltage ranges? And what features in these curves reveal the underlying electrochemical processes? What does the shape of the curves indicate about the intercalation and deintercalation kinetics of sodium ions within the non-IO2 structure, and how do these kinetics change as the voltage range is varied? How do the differences in voltage plateaus or slopes across the various voltage ranges inform us about phase transitions or redox reactions occurring in the material? In what way does the C/10 current rate affect the resolution of these features, and what can be inferred about the reversibility of the reactions from the curvature during charging versus discharging? How does the specific capacity measured from these curves compare when operating in different voltage windows, and what role does this play in determining the optimal operating range for the material? How might the observed hysteresis between the charge and discharge curves be related to energy losses or resistive components within the electrode, and what does this imply about the efficiency of the non-IO2 cathode material? What insights can be gained about the stability and durability of the electrode by investigating the evolution of the curves over repeated cycles, and how do these changes correlate with any degradation mechanisms or structural changes? What?